time I'm ever teaching numerical.
Are we gonna have another test in there?
Yeah, at some point.
Or a quiz?
What the heck just happened? Your next one will be over the stuff that we're gonna do next.
Can we not have a quiz about cubic splines?
We are not having a quiz over cubic splines. Literally, that major assignment that you're gonna do. That's it.
Okay.
Period. Done. What's that?
What if it doesn't work?
But except for the extra credit opportunity that also involves cubic splines, but that's the plan. All right. How's it going? Meh. Meh. It's Friday.
Yeah, it is. We have to do this fundraising thing for soccer, and it's at Busch Stadium.
Oh,
and
okay.
So we have to leave by 6:45 tomorrow in the morning, and we won't be back till 7.
Ugh.
So
It's a long day.
I know. It's
Did
really
you do something
long.
with the Rams? Maybe you weren't here yet. They said one of the Rams were still in St. Louis, but yeah, they haven't been.
Yeah, I just think it's stupid. I mean,
They did something then too, but it must be kind of similar, I'm guessing. But yeah, it seems like a long day.
yeah, and we're supposed to be there at like an hour and a half before gates open, which is I think like 10:15. So I don't know why we're leaving at 6:45 either.
Yeah, that's a long time to.
I
Yeah.
asked my assistant coach, and he was like, "Oh, I'm accounting for traffic." But I was like, "I don't think there's really
Well,
traffic at."
Not that early in the morning. You get there plenty of time, plenty early. All right. So, are there any questions about the checking of the distributions, the making sure that we got distributions that fit the data? Goodness of fit tests. That's what the word I was looking for. Talking has not been the strong suit today. All right. Well, so today we're going to talk about what are referred to as contingency tables, and same idea that we just talked about with goodness of fit tests. What we're going to see is a chi-squared statistic. So essentially these contingency tests, the contingency tables tests that we're going to do are similar to what we just did in the previous section. It's still going to be a chi-squared test. We're going to do one more type of test in this chapter. I'm going to just do section 8.5, and then the rest of the semester will be spent in chapter 10 with the more theoretical stuff at the end. So we're almost done with the different types of hypothesis tests that we're going to do. When do we have a test scheduled again? Does anybody remember?
It's like
Is it
it's like celebration of
scholarship week? So it's after the week after Easter.
I think it's like before the 27th. 27th is Saturday.
Okay, sure. Yeah, I think you're right. Yeah, the 25th.
24th.
25th. Okay, but it's whatever that week is after Easter. Then okay. Yeah. All right. Anyway, contingency tables. So let's just look at a specific example. Let me get my glasses out so I can actually see. This is just problem number one. There's basically two different ways that things could be set up for these contingency tables, but the test is going to be exactly the same. So we've got, this is number 1, 8.2-1. We have two groups. Each of which can be divided into 6 categories. Oops. All right, so these are the numbers that they give us in this problem. All right, so you've got 500 total things. They're split into 2 groups. And each of the groups, you can fall into one of 6 categories. So the first type of contingency table that we can do is that, well, certainly it looks like for each group, it's a lot more likely that you're going to fall into category 1 and category 3 than any of the other categories. So the hypothesis test isn't saying that we're equally likely to fall into one of the 6 categories for each particular group. That's not what the hypothesis test says. That would be a goodness of fit idea, that you could say the probability is 1/6 for each one and see if you can do a good fit with that binomial distribution idea. Yeah, you could do that, but that's not what this one's saying. What this one says is that, notice that this is high for group 1, this is high for group 1, it's also high for group 2 in the same spots. So the hypothesis test is that whatever the probability is that you land in category 1 for group 1 is the same as the probability that you land in category 1 for group 2, and so on down the line. So the hypothesis test is that the H0 is that PI1 is the same as PI2 for I equals 1 to 6. And then your alternative hypothesis is that that's not true. At least one of the probabilities is different. So the notation here is, of course, the first subscript is the category, and the second subscript is the group. But again, the idea here is that it's not equally likely. Whatever the probability is that something is in category 1 for group 1 is the same as the probability of being in category 1 for group 2. Almost like it's a homogeneity type of condition. That however they're spread out in group 1, it's spread out the same way in group 2. Does that make sense? All right. So, if these are our categories, how would we get the expected values? What would we expect to see in each one? Well, all I have are relative frequencies of being in each category, right? In this first category, there's, I think that's a 53, there's 148 in that category 1, right? So if these probabilities are going to be equal to each other, what would be a good expectation be for the probability that you fall into group 1? If they're supposed to be the same, what would be a good estimate for what the probability should be? Well, how many total things are in category 1?
95 over 148. Yeah, 53 over 148.
Well, except that we want to make sure the probability is evenly split, or the same. So certainly 95 over 148 and 53 over 148 are really, really different, right? So if we want to make sure we want to try to evenly split up the probability, we know there's a total of 148 in category 1. How many total things are there? 500, right? So what would be a good estimate for the common probability then? Yeah, 148 over 500, right? So our guess for our estimate, if you will, for P11 equals P12 should be the 148 over the 500. And then you would do the same thing for the other categories. So if we wanted the expected number, in group 1, category 1, what would be the expected number of things that using that probability, what would be your expected number of things in group 1, category 1? How would you find that? Apparently quietly. How would we do that? How many total things are in group 1? Yeah, total things in the group 1 are 300, right?
Yeah.
What's the probability that you land in category 1? 148 over 500, right? So how would you find the expected number? Multiply them, yeah, exactly. So you would take your 300 times the 148 over 500. That would give you your expected number. Does that make sense? Right? So again, we're basically what we're doing is we're pooling everything into category 1 together and making an estimate for the common probability. Once we've got an estimate for the common probability, we're going to calculate expected numbers, which is what we did in the chi-squared statistic for the goodness of fit, right? Right? We had observed and we had expected. It's the same thing we have here. Our big table here is observed. What we're trying to do is making an expected table. Okay? So you would do the same thing for all of the categories. So just what would your expected number be in group 2, category 1? What would you have? It'd be the 200 times the probability, right? Okay, so what we'll do from our totals in the table, we will make an expected table. So we'll have observed number in each category. We'll have expected in each category. So then we can do the same chi-squared idea that we just did in the previous section. We can do observed minus expected squared divided by expected. That gives us approximately chi-square of 1, right? Now, we get a little bit different here as we go across the tables. We'll talk about degrees of freedom here in a second. But let's just see how we can set up the Excel sheet. I don't have these typed in. Sorry. Luckily, there's not a lot of numbers, so we can type them in together here. It wasn't like some of those ones that were in the previous section that had like 100 in them. All right, so let's start a new workbook here. Let's not get hooked up. There we go. Hello. There it goes. All right. So the numbers we need here are 95, 53, 36, just typing these in. Oops, typed in the wrong number. And I'm also just using the sum command to total these things up here because I need them. Oh, hush. All right, so in right below here we'll do expected. So in this cell, so I've got all the things typed in from the original table. In this cell, I want to use this sum divided by the total times the 300 to give me my expected values, right? So when I type this in, I want to do A3 divided by G3. I don't want to change, I want to use an absolute cell reference on the row but not the column because I want the column to change as I copy across. But when I copy down, I don't want the cell reference to change. I want absolute cell reference on G3. And then I want to multiply that by G1, and I want to keep the column absolute reference, but not the row, because I want to be able to copy this down to get the second row. So again, here we want A3, and then absolute the row, because I don't want the row to change when I copy it down. I want to multiply it by G3, absolute the whole thing, because I don't want that one to change at all. Oops, sorry, not multiply, divide. That's what gives us our estimate for our probability in that category.
Did you maybe zoom? Sorry, I didn't wear my glasses.
Oh, seriously, Susan?
Okay.
There we go. Sorry about that. I should have zoomed in. I forgot. A3, absolute the row, because I'm going to copy this down to a second row to get the second expected values. And if I copy it down, I don't want the row to change. Okay, but I do want it to change as I copy across. So I don't want the column absolute cell reference there, right? Because we have different totals for each category. Okay. Divide by the total. That one I do want an absolute cell reference. I don't want that one to change ever. And then multiply by the number that's in a group. I do want absolute reference on the column, but not the row, because I want the row to change as I copy down. I want the row to change as I copy down, but not the column to change as I copy across. We good with that? All right, so let's copy this over and copy it down. So far, so good?
So what are those numbers again?
Those are expected values.
For both groups?
For both groups, yeah. So the 88.8 is the expected, if the probabilities truly are the same, then we would expect to see 88.8 in group 1 in category 1 and 59.2 in group 2 category 2. The setup for this problem is that two different groups of nurses distribute their time in similar ways. That's the setup of the problem. The exercise 3 has a setup of different methods of instruction for standardized tests. So anyway, so now we want to make a chi-squared statistic out of this. So what we need to do is we need to take our observed, so that's up at A1, minus the expected, which is down here in A5, square it, and divide it by the expected. Is okay? All right. So then we just calculate all of these. Oops. And add those up. So we'll do, oops. If I could type, that would be very helpful.
And those are the probabilities.
Those are the each chi-squared statistic individually. Yep. Okay, so that's our chi-squared statistic. The last thing we need to do is compare this to some critical value or equivalently find a p-value, right? To see whether or not we reject the null hypothesis. To be able to do that for chi-square, we have to know how many degrees of freedom we have. Right? All right, so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 things that we calculated here, correct? However, we lose 2 degrees of freedom off the top, because once I know these 5, I know the last one, right? Everything has to go up to 100% essentially, correct? Okay? Well, I should be pointing at these when I do that, right? I have 5 degrees of freedom for that one and 5 degrees of freedom for that one. I lose 1 for both of them because it's completely determined. Once I know the other 5, I know the 6th, right? So we lose 2 there. And then remember, every time you estimate a parameter, you lose a degree of freedom. Right? Okay? So in this case, how many parameters do we have to estimate? Now again, I don't really estimate this one because it's determined once I pick the other ones, correct? But I do have 1, 2, 3, 4, 5 parameters that we estimate here. Right? Because each of those were estimated by pooling. Okay? So we lose another 5 degrees of freedom here. So there's only 5 degrees of freedom total. Does that make sense? Okay. So when we do this and want to calculate the p-value, we do the chi-square distribution right tail. Here's your x value. 5 degrees of freedom. So you get 0.6645, which is a huge p-value. So we would not reject. So it does seem like there's evidence that the nurses really do distribute their time somewhat equivalently. Does that make sense? You okay with that? So the second part of this problem, which is not really a second part, it's what happens if there's a third group of nurses with another distribution.
So that 0.66 is a p-value.
Is a p-value, yeah. And again, a high p-value means that we really don't reject the null hypothesis. So we really do have some evidence that they really are distributing their time similarly. Maybe not equivalently, but similarly. Yeah. So in problem 2, they give you a third group of nurses with distribution 130, 75, 136, 33, 61, and 65. And I need to go in and edit my formula here. So notice that I've got to also go in here and get another. Oh, hey, not there. Here. I need to do another expected idea. So let's see. That one still looks okay for the formula, right? We're taking A4, taking the A4, dividing it by the G4, and multiplying it by G1. So that looks okay. So I should just be able to copy this bottom row down.
Your G4 should be 1,000.
Oh, yeah, it should. Thank you. Yeah, that's better. That's better. Thank you. And then we should have one more row to add in here. So is this doing this correctly? A2 minus A7 over A7, A1 minus A. Okay, so everything is good there. So I should just need to move this down. And then edit this formula to make it 12. Okay. So what was this? I know I did that rather quickly, so let me talk about it again here. I put in an extra row for the other distribution that they gave us to see if this other group of nurses was distributing their time similarly to the previous two groups of nurses. Okay, so I added in that extra that extra row, still calculated the sums in the same way that we did, especially after Sydney corrected me. Okay. And then did the expected values by pooling again. So this first column should be the 278 over the 1,000 and then times each of the totals. And then this array here is again observed minus expected over squared over expected. So that's what those values are. And then this 10.17 is just the sum of that entire array. Now the chi-squared statistic is the chi-squared statistic is right. The p-value is wrong because I didn't change the degrees of freedom yet. How many degrees of freedom do we have here? How many degrees of freedom do we have? Are we able to get the table set up correctly? Let's put it that way first. We okay with the tables? Okay. How many degrees of freedom do we have? Apparently none. Very quiet about it. Well, count them like we did the last one. For each row across, how many total do we have? Okay, so there's 6 rows across, but remember again, the last category is completely determined. So degrees of freedom across each row is what? Yeah, so 15, good. We got 6 total categories, but this one's completely determined once we've got the other 5, right? Because the rest of the people have to fit into the last category. Right? If it's not 1, 2, 3, 4, or 5, we know it has to be 6. So there's a degree of freedom that's off there. Okay? And then we've got the 3 rows, right? So we've got 15 here. How many parameters are we estimating though? 5. So we have to subtract off 5 because of the 5 parameters we estimate. So this degrees of freedom should be 10, not 5. So go back and edit that to 10. P-value went down, but it's still high. So does it appear that this other group of nurses also distributes their time similarly? Yeah. So that's the idea for that one. Oof. That okay? All right. So the other type of way that we can use contingency tables is similar to what we just did, but it's going to test independence of variables rather than do you have 2 different groups and are they have similar probabilities of happening in each category. So let's look at 8.2-5. We have a population that's separated into male and female, and then whether or not they favor, oppose, or have no opinion on smoking in public areas. All right, so these are the values. $231, $205. I wonder if it's one of those where you had to text or call in to say that you have no opinion. I love those things. I want to call you to tell you that I have no idea. Let's just, ooh, hey, there's a lot to add up. I mean, I could have typed these numbers in so they had them in the book, but I'd rather just do the sums. Okay, so we've got two groups, male and female. 3 opinions. I'm for it, I'm against it. I don't have an opinion. So what we want to know is gender independent of opinion? That's what we're going to test in this case. So we're going to test independence of the variable. So one variable is gender, one variable is opinion, and we're going to test whether or not those variables are independent of one another. The way we're going to do that is the same way that we just did the previous 2 things that we've done. We have observations, right? We have how many things have been observed. We want to figure out if they're independent, what would we expect? We need expected values. So the idea behind independence, of course, is what? If I take the probability of the and, if I do the probability of A intersect B, if they're independent, how do you find the probability of A intersect B? What do? You do the probability of A and B. If they're independent, how can you find that probability? Let's multiply them together, right? So if they are truly independent, then we should be able to find the probabilities of each just by multiplying them together, right? So if I want the probability that's, if I want this probability that's right there for males who favor smoking in public places, I should be able to do probability of male times probability of favor, right? We agree? Can we figure out probability of male and probability of favor based on the table? Yeah. Here's probability of favor, right? 564 over 1015. Okay? I can do probability of male, 503 over 1015. And then I can do the probability of A and B by multiplying them together. And then if I want an expected value, I can just multiply it by the total. Right? So I would do 564 over 1015 times 503 over 1015. That would give me that should give me probability of male and favor, right? That's the intersection. And then I want expected value, so I would multiply by the total. Well, the total is sitting right there at 1015, right? So I just need to do the 564 times the 503 divided by 1015. And then all the way across for your table. So if we want to do expected values now. Oh, I didn't zoom in again, did I? Maybe zoom in. All right. So if we do expected values here, this one needs to be the 564. I want that to change as I go across the rows, but not, as I go across the columns, but not down the rows. So I want to put an absolute cell reference on the row. I want to multiply it by the 503. This one I want it to change as I copy down a row, but not across the column. So I'll put an absolute cell reference on the column. And then I want to divide it by the total. And that one I want absolute cell referenced in both spots. The reason why, again, that's the formula is because we're doing 564 over 1015 for probability of favor. we're doing 503 over 1015 for probability of male, multiplying them together for independence, and then multiplying by the total to get expected value. So the total cancels out one of those 1015s in the denominator. That's why we just have it divided by E4, and that's it. Right? So then I should be able to copy this over and down. And then do our same thing that we've done previously. Observed minus expected squared over expected. It's not becoming a little more clear that chi-squared statistic is pretty important. Because it's being used in all sorts of scenarios here, right?
Dr.
Yeah.
Can you go back to what's in B6? I actually didn't know that.
Oh, okay. That okay? You get it? Okay. All right, so now we add this up. That's our chi-squared statistic, the 5.976. All right. So far, so good? So now we need to calculate number of degrees of freedom. So let's think about number of degrees of freedom here. So we've got all of these different categories, right? Now again, in this case, we've got all of these categories for the. We're thinking about dividing this total here into all of these categories. So really, we've got 1, 2, 3, 4, 5, 6 total places, but only the very, very last one is completely determined by the other 5. Okay, so I lose 1 degree of freedom out of the total for that. But then we also lose degrees of freedom for estimating parameters, right? So when we estimate these things, how many estimates do we make?
4 or 2.
Well, it looks like, I think 4 was right the first time. It looks like 6, right? But really we're not estimating 2 of them because 2 of them are determined by when you're done, correct? They're the ones that are left over. So in this particular case, we had 6. Oh, hey, that marker's just got all sorts of dead. We had 6 total things, right? Subtracted off 1 because the one's the leftover part of the total, correct? And then minus, what, 4 for the, is that really true? 4 for the number of parameters? That's, seems like we're subtracting off too much. Because we get 1 degree of freedom? I don't think the degrees of freedom is 1. I think it's supposed to be 2. What am I counting wrong? What am I counting wrong? K plus H. Oh, wait. It's not 4. Hold on. No, it's not 4. Sorry. That's the problem. I've got probabilities as I go across here, right? There's 3 probabilities as I go across, but really only I calculate 2. Right? There's 2 probabilities as we go down, but really we only calculate 1. So we only really calculate 3 of the probabilities, right? So to write it in general, if I have m rows and n columns, you have m times n minus 1. That's number of slots for your total, right? And then you subtract off, I've got probabilities to go across and probabilities to go down. So you would have to go down and across, but really 2 of them aren't really calculated. The good news is that this factors nicely. That's probably the easier thing to remember than going through it all. You get m1 minus 1 times n minus 1, which is really what you get here, isn't it? 3 minus 1 is 2, 2 minus 1 is 1, 2 times 1 is 2.
So, but we wouldn't use that for the last problem, would we?
No.
So what kind of problem is this?
This is testing independence.
Testing.
Yeah, we're testing independence in this case. So yeah, we get a different... No, actually, we get the same thing for that one too. I mean, it's the same number of degrees of freedom for the last one as well. It turns out to be that same thing.
N minus 1, N minus 1.
Yeah, we got the same number of degrees of freedom there too. In the first one, we had 5, which was 6 minus 1 times 2 minus 1. And in the second one, we got 10, which is 6 minus 1 times 3 minus 1. It's the same number of degrees of freedom for both.
Use it on
Yeah.
any of them.
We get the same one. So this is chi-squared right tail with 2 degrees of freedom. Ooh, hey, almost rejected at 0.05. Almost. At 0.1, you would reject and say that they are independent. That's what we're trying to do. Sorry, they're not independent. Independence is the null hypothesis. That was what we used to estimate the parameters. Does that make sense? And then all of these are the same type of problem. You want to see another one? Sid says yes, but sometimes he does this and says no. All right, let's do. What's that? I did. She said, well, she actually said it yesterday, though she shook her head one way and, yeah, no. She actually said no when she was shaking her head yes. Like, that was really weird. All right, let's look at, yeah, we'll do number 11. There's a little bit more data in this one. So in this one, they're going to rank a roommate and then against grade point average. So the rank of roommate,
What problem was this?
this is number 11. So the roommate rank is 1 through 5. Let me add another row here. And then we'll have GPA across. So this will be under 2, 2 to 2.69, 2.7 to 3.19, and then 3.2 to 4. Oops. I don't know why I wrote it that way, but that's all right. 8, 5, 6, 3, 1. So 1 is they're a bad roommate, difficult to live with, and discouraged scholarship. 5 is congenial and encouraged scholarship. Oops, that was weird. Oh, I need to zoom in again, don't I? You really got to start yelling at me. 9, 11, 7, 5, 3. Well, you can see what I've been starting to wear mine more. One of those things that happens when your eye get older and your eyes decide to take a powder or something. All right, 4, 11, All right. So then we'll put the totals on the end and at the bottom here. Well, it used to be that I would just get a headache when I would read, so I needed glasses. And now it's gotten to the point of I can't see crap up close. Yeah. What did I just do? No, that's right. It wants me to put the label in there, and I don't want the label in there. All right. Must have typed them in right because the totals are calculated correctly. Okay, so those are our observed values. So again, to get the expected ones, remember for each one, we're going to do probabilities. So in this upper left-hand corner, I'll use the 23, the 31, and the 200. All right, so we'll have 23 times the 31 over the 200. But we'll do that with cell references. 23, I don't want to change the row. Obviously, I don't want to change the row. If I copy that down, I'm going to be into weird rows, right? I want to multiply it by the 31. Don't change the column. I want to divide that by the total. Don't change it all. So for this one, I should have B8 times F3 over F8 with the appropriate cell references. Did we get the formula? If I hit enter, is that okay? Yep. No, too late if it's not. Copy over, copy down for the same size. And then we add those up. Oh, no, we don't. Not yet. Sorry. Those are expected values. I got to do... Forgot. I got to do observed minus expected first, don't I? So I need to do B3 minus B10 squared divided by B10. I got to do the observed minus expected divided by expected. I would have had a huge chi-squared statistic. I had forgotten that step. Now copy that down and then add that up. Ooh, that is a huge chi-squared statistic anyway. Which isn't a huge surprise because, again, we're saying the test that we're saying is that being a bad roommate and having whatever your GPA is are independent of each other. So you can be a crappy roommate and have a high GPA, or a good roommate and a low GPA. Not that there aren't exceptions to that, but you're probably not encouraging scholarship if you got a GPA below 2, for example. Right? Which is, notice I said that specifically because that's where one of our highest values is in the chi-squared statistic, isn't it? All right. But to find the p-value here, I need to know the number of degrees of freedom we have. How many rows are there? 5. And how many columns? 4. So we would do 4 times 3. So there's 12 degrees of freedom. Does that make sense? And we got a p-value of 0.02. So we would reject the notion that the variables are independent. Which, again, not a huge surprise. Does that make sense? There? Cool. Like I said, the last thing we'll need to do is one more hypothesis test. The hypothesis test we're going to talk about next is about the median. So we're going to do what's referred to as a assigned rank test. So we'll talk about that next time. And then I'll give you a homework over those 3 ideas. I don't have to do that? All right. Have a good weekend, everybody.